Good morning, cadets. In the previous session, we discussed about potential energy of a system of charges placed in a electric field. Potential energy of two charges placed in an electric field, right? We are now continuing that application. Potential energy of a dipole placed in an uniform electric field. Okay. Potential energy of an electric dipole placed in uniform electric field. So, let us draw first the uniform electric field. Uniform electric field is represented by parallel field lines. So, these parallel field lines, let us say that the uniform electric field is acting along the x-axis. It is acting along x-axis. So, this represents uniform electric field. Now, let me take an electric dipole and keep it with certain orientation. Suppose this is an electric dipole with its dipole moment. You can see the dipole moment is always directed from negative charge to positive charge, and this is the dipole moment vector P, directed from negative charge to positive charge. And we know the dipole is of length 2a. It's of length 2a. This dipole is placed with certain angle of orientation theta with respect to the electric field. 2a is the length of the dipole, as we have seen earlier. Length of the dipole from minus q charge to plus q charge is 2a, right? Now, when a dipole of dipole moment P, dipole moment P is given by 2a into q, where 2a is the dipole length and q is the magnitude of either of the charges. The product of dipole length and q, the charge, gives us dipole moment directed from negative charge to positive charge. When such a dipole is placed with certain angle theta with respect to electric field, we have studied earlier that this dipole will be experiencing a torque due to external electric field. The external electric field here is uniform electric field, right? The torque is because of, we have studied, it experiences an equal and opposite force. The positive charge experiences a force along the direction of electric field, and the negative charge experiences force minus F, equal and opposite force, in the opposite direction of electric field. As a result, when equal and opposite forces, a pair of equal and opposite forces are acting on a dipole, it leads to a torque. And the tendency of this torque is to turn this. The tendency of the torque is to turn the dipole and align it along the direction of electric field. So, as a result, if you leave it, because of this torque, the torque which is acting now, the torque is the clockwise torque, you see, clockwise torque. The clockwise torque tends to align this dipole moment along the direction of electric field. As a result, the dipole aligns along the direction of electric field, this. And once it aligns along the direction of electric field, then it will become stable. So, we have studied the torque exerted by electric field, right? The torque exerted by electric field is given by torque tau equal to P cross E. This also we have derived earlier, which is given by Pe sin theta, and it is clockwise torque in this case, clockwise. Now, we want to derive the expression for potential energy stored in a dipole in a uniform field. So, for that we need to do work against this torque. Let us exert an external torque in the opposite direction. We are exerting an external torque. This is the torque exerted by electric field. Now, we are exerting an external torque to external, which is exactly equal to the torque exerted by electric field, but in the opposite sense. We are exerting counterclockwise. When we are exerting counterclockwise torque, which is exactly equal and opposite to the torque exerted by the electric field, then the dipole turns with a small angular displacement. Let us say the dipole is turning with a small angular displacement. Suppose this is how it is turned, through small angular displacement d theta. Then now we can calculate what is that work done, small amount of work done in turning this dipole moment through a small angular displacement d theta, right? Small work done. Small work done dW by exerting external torque is given by tau external is equal to tau external into d theta. You see, in case of linear motion, we have seen that the work done is equal to force into displacement, whereas in case of rotational motion, turning motion, the work done is calculated as torque multiplied by angular displacement. Force is replaced by torque, displacement is replaced by angular displacement, right? So, this is the small amount of work done for the rotational motion of the dipole moment or dipole to turn it through small angle d theta. Now, how much is this external torque? Tau external is equal to, you see, the tau external is equal to exactly tau exerted by the electric field. The magnitudes are equal, but it is in the opposite sense. If you take them as by vector notation, you know torque is a vector. So, tau external is exactly equal and opposite to tau exerted by the electric field. So, that when the torque external torque is exerted, the dipole should not undergo angular acceleration. The dipole should move with infinitesimal small angular velocity, or angular speed, constant speed. So, there should not be angular acceleration. With that condition, the torque exerted must be exactly equal and opposite to torque exerted by external electric field. So, that we can now substitute what is the value of this torque exerted. So, torque exerted is, if you take magnitude torque exerted magnitude becomes Pe sin theta. Now, just substitute this value. Therefore, dW is equal to Pe sin theta d theta. Now, this is for a small angular displacement. Suppose we are turning it from initial angle theta 1 to some final angle theta 2 through through considerable large angle, then we need to calculate total work done in turning the dipole from theta 1 to another angle theta 2, where we have to do large amount of work. So, in that case, what happens? The torque that we are exerting will be not constant. The torque will be depending on, you see, torque will be depending on Pe sin theta. P is the dipole moment is always constant, electric field is uniform and it is also constant. Only changing value is the angle of orientation. As the orientation angle of the dipole with respect to electric field changes, the torque exerted should also change, right? Therefore, when we calculate total work done in turning the dipole from theta 1 to theta 2, we have to integrate from theta 1 to theta 2 to get the total work done. So, total work done in turning from theta 1 to theta 2, we write it as total work done W is equal to integration of dW from theta 1 to theta 2. Substitute the value of dW. So, value of dW now becomes theta 1 to theta 2 Pe sin theta d theta, Pe sin theta d theta, because this is Pe sin theta, which is nothing but tau external, that is substituted as Pe sin theta d theta. Now, Pe being constant, I will take it out. Pe, now integration of sin theta becomes minus cos theta, and upper limit and lower limit is theta 1, upper limit is theta 2. This becomes the total work done, right. So, thus I will take out this minus sign outside. This total work done is now written as minus Pe cos, minus Pe I have taken it as outside, minus Pe. Now, theta 2, first we have to substitute upper limit cos theta 2 minus, then you have to substitute lower limit cos theta 1. So, this becomes the expression for the work done. So, this work done is stored in the dipole as difference in potential energy from initial angular position theta 1 to final angular position theta 2. When the dipole is turned through initial angle theta 1 to final angle theta 2, let us say final angle theta 2, it is stored in it in the form of potential energy difference. So, this I am calling it as potential energy difference. Potential energy difference, I am writing it as delta U. Delta represents change in potential energy or difference in potential energy. So, this delta U, therefore, I will write it as equal to U2 minus U1, final potential energy minus initial potential energy. So, this is nothing but PEF, final potential energy, minus PE potential energy. PE means potential energy, right? Potential energy, final potential energy minus initial potential energy. So, from the above equation I can write what is final potential energy. Take minus here, minus PE cos theta 2, that becomes the final potential energy when the dipole is turned from theta 1 to final angle theta 2. Now, keep this minus as it is and take this minus Pe cos theta inside the bracket, minus Pe cos theta 1. Purposely I have written so that you can note down here. This I can keep it as one bracket, second one I can keep it as another bracket, so that this bracket you can see can be written as U2 and the second one can be written as U1, where U2 corresponds to minus Pe cos theta 2, U1 corresponds to minus Pe cos theta 1. Therefore, we get finally final potential energy UF or U2 is equal to minus Pe cos theta 2, Ui initial potential energy as minus Pe cos theta 1. So, in general if you take expression for potential energy at any angular position, any angular position can be now written as U at any angle theta. U at any angle theta can be now written as minus Pe cos theta, minus Pe cos theta, where minus P cos theta, theta corresponds to the angular position, right? And the same thing can be now written as minus P dot E. So, u theta can be now represented as minus P dot E. So, dot product of dipole moment and electric field gives us the potential energy stored in the dipole, whereas the cross product gives us the torque exerted, right. So, this is how we discuss the potential energy of a dipole placed in an external uniform electric field. Now, one interesting thing to be noted here, right. When the dipole is just left as it is, the dipole aligns along the direction of external electric field because of the torque exerted by the external electric field. At that moment, what is the electrostatic potential energy stored in the dipole? The electrostatic potential energy stored in the dipole, that moment becomes minimum, and when it possesses minimum potential energy, then the dipole is in stable equilibrium. It will not rotate further. The dipole will be in stable equilibrium, and it will possess negative potential energy, that is minus Pe, right. Let us discuss these cases in detail. Therefore, we can conclude that the work done in turning the dipole in an uniform field is stored in it in the form of electrostatic potential energy. So, in general I can write electrostatic potential energy at any angle theta as equal to minus P E cos theta. So, minus P E cos theta, which is also written as minus P dot E, right. So, we also got a very important equation, that is difference in potential energy delta U is equal to U2 minus U1 as equal to minus Pe cos theta 2 minus Pe cos theta 1. So, these are the important equations for difference in potential energy and potential energy at any angle theta. Now, if look at this, this is the most general equation which you are very much interested, which we are interested. If first case theta is 0 degree, then if you substitute in this first equation, okay, equation of the potential energy, u at 0 degree is equal to minus Pe cos 0. So, minus Pe cos 0 gives you minus Pe, which is minimum potential energy, which is negative. So, it is possessing negative minimum potential energy, and this minimum potential energy leads to stable equilibrium position, stable equilibrium state of the dipole. So, this is the case when the dipole is aligning along the direction of external electric field like this. When P, you see P and E are in the same direction. Now, let us see the second case. If theta is 90 degree with respect to the electric field. Theta is the angle between dipole moment and electric field. The angle between dipole moment and electric field vectors is angle theta. If theta is 90 degree, means if P is vertical to electric field, now look here, this is 90 degree, then what happens? Then the potential energy at 90 degree, potential energy at pi by 2 theta equal to pi by 2 becomes minus Pe cos 90. Cos 90 is 0. So, it becomes 0. So, 0 does not mean that it is having minimum energy, because minimum energy is minus Pe when it is aligned along the direction of external electric field. But when the dipole is turned, when the dipole is turned through 90 degree, then it is having 0 potential energy, but 0 potential energy does not mean that it is minimum energy, it is having some energy. As a result, the dipole is not stable. Dipole, the moment you release, the dipole tends to turn along the external electric field because of the torque exerted by the external electric field. Therefore, the dipole is not stable. So, we can write here, the dipole is in unstable equilibrium position. The dipole is in unstable equilibrium position. Now, third case, let us see. If the dipole is turned through 180 degree, if the dipoles, see here, this is electric field, and if the dipole is turned through 180 degree, suppose the positive charge is brought here and negative charge is brought here, so that it is turned by 180 degree. Now, this becomes the direction of dipole moment. Then when the angle is 180 degree, then what happens? U at 180 degree, if you just substitute, it becomes minus Pe cos 180. Cos 180 is minus 1, minus of minus becomes plus Pe. So, it has maximum potential energy. So, U max is equal to plus Pe. So, when the dipole possesses maximum potential energy, it is said to be most unstable position, most unstable state. As a result, the dipole immediately turns with maximum kinetic energy, and aligns along the direction of external electric field. Therefore, it is said to be in most unstable state of equilibrium. So, this is how we discuss about the potential energy of a dipole placed in an external electric field. So, when the dipole is perpendicular to the external electric field, this is the external electric field and dipole is perpendicular like this. Suppose the dipole is held like this, then the angle between electric field and dipole is 90 degree. That becomes the position of 0 potential energy, right? 0 potential energy is not minimum potential energy. 0 potential energy is having more potential energy than the stable equilibrium position, Pe times. Therefore, 0 potential energy is unstable state. The moment you release it, the dipole turns with a certain velocity. So, potential energy is converted into kinetic energy, right? Now, let us derive the same equation with the concept that we have learnt in the previous session. Potential energy difference we will calculate with the values of actual potentials at those positions of positive charge and negative charge. We can derive the same expression by another alternate method. Right? Let us see this alternate method. We have derived yesterday potential energy of system of two charges in an external field. yesterday we had derived U is equal to Q1 V1 plus Q2 V2. This is what we have derived yesterday. Q1 V1 plus Q2 V2 plus Q1 Q2 by 4 pi epsilon naught R12, where R12 is the distance between the charges, right? This is the equation that we have used in the previous session. Now, let us consider what is V1 and what is Q1 here. Let us consider Q1. Let Q1 be equal to plus Q charge at position R1, and potential at that position due to external electric field, VR1. Let us take that potential to be VR1. Similarly, Q2, let us take Q2 to be equal to minus Q charge, and let us assume that this is at position R2. And the potential at R2, let us write it as VR2, or we can write V1 V2, that is also better. So Q1 V1, Q2 V2, that would be a better option, right? So let me write potential at that position, let us write it as V1 here, and here let us write it as V2, exactly at position R1, exactly at position R2 respectively. Now I can substitute this, and before that I can write what is Q1 Q2 upon 4 pi epsilon naught R12. Here R12 is the distance between the two charges. The distance between two charges is 2a. R12 is equal to 2a, right? And the product Q1 Q2 becomes Q square. So the last term becomes very simple, Q square upon 4 pi epsilon naught 2a, right? Now we will write this term, Q1 V1 plus Q2 V2 is equal to Q1 I have taken it as plus Q charge, V1 as I have written it as V1. See here, Q2 is minus Q, and the potential here is V2, Q1 V1 minus Q2 V2, because charge is negative here, minus Q V2, right? Then, yes, now we will substitute the value of this one. If you take Q common, then Q becomes V1, Q into bracket V1 minus V2. So this we will substitute in this equation. Therefore, U is equal to Q into bracket V1 minus V2, and this one, as I told you, Q1 is equal to plus Q and Q2 is minus Q, so it becomes minus Q square upon 4 pi epsilon naught into 2a, where 2a is the dipole length. So let us substitute what is V1 minus V2. V1 minus V2, look at the diagram, is the potential difference between the potential values. This I have taken it as V1, and this I have taken it as V2. You see, when you draw perpendicular planes, the perpendicular planes to the electric field represent the equipotential surfaces. Here is the equipotential surface of value V1 here, and this is the equipotential surface of value V2. So I want to find out the difference in potential between V1 and V2. So V1 and V2, if you take the difference, that gives you potential energy potential difference. Here V1 minus V2 gives us potential difference, let me write it as dV. dV is the potential difference, that is I can write it as potential difference. So we know the value of electric field. Throughout the space, the electric field is uniform and it is constant. So we know the relation between electric field and the potential difference. So I can express this potential difference in terms of electric field. So we know that electric field E is equal to dV by dl. E is equal to minus dV by dr, dV by dr, dV by dr, negative potential gradient. This is what we have derived in the earlier videos. Electric field is negative potential gradient. Electric field is change in potential per unit displacement perpendicular to the direction of the equipotential surface. So therefore I can write what is dV. dV is therefore equal to minus E dr, where dr is the distance between these two. What is the distance between these two? That can be found out. See here, this is the distance, perpendicular distance, either you take from here to here or this one. This is the perpendicular distance, whatever. So we know the angle of orientation here is theta. So if this is angle of orientation, this is also angle theta, and we know alternative interior angles are equal. So this angle is going to be theta. So when this angle is theta, and we know what is this length is 2a, dipole length is 2a, then we can find out this dr. What is this dr? dr will be very easily written as 2a cos theta, 2a cos theta, because from this right angle triangle, you can just see from this right angle triangle, what is cos theta? Cos theta becomes equal to side length. Side length here is r2 minus r1. r2 minus r1 is dr divided by the hypotenuse. The hypotenuse is 2a. Therefore dr becomes equal to 2a cos theta. So I can substitute the value of dr. So thus it becomes minus E into 2a cos theta, minus E into 2a cos theta. Now we can substitute this dV in this equation, above equation. Therefore finally u becomes equal to q into dV. dV is minus EA cos, minus E into 2a cos theta. So this is dV minus q square upon 4 pi epsilon naught 2a. Yes, now this can be modified now. So when you modify this, you see it can be written as 2aq. We know what is 2aq. 2aq is P. So thus I can write it as minus, take the minus outside, right, minus into 2aq, 2aq into E into cos theta minus this term q square upon 4 pi epsilon naught into 2a. So this becomes the expression for potential energy. Now when we derive this potential energy using this previous concept of a system of two charges placed in an electric field, we get an additional term. This additional term q1 q2 upon 4 pi epsilon naught r12 is nothing but minus q square upon 4 pi epsilon naught 2a. This is due to the interaction between the plus and minus charge, interaction between the plus q and minus q charges, due to which we get this term, but this term is going to be very small, a very small term, and this very small term most of the times it is ignored, it is neglected. So, when you neglect this, you are left with potential energy is equal to minus P e cos theta. So, minus P e cos theta minus of this one. So, finally, we can write the potential energy as U equal to minus P e cos theta. Therefore, finally, it becomes minus P e cos theta. Therefore, U is equal to minus P e cos theta, ignoring the term minus q square upon 4 pi epsilon naught into 2a, which is very small, that is due to the interaction between the two charges plus q and minus q. So, you are left with this one. Therefore, finally, we get U is equal to minus p vector dot E vector. This is the expression for potential energy of a dipole placed in an uniform electric field. Okay. So, I have derived this by two methods. Okay. Go through them, practice them. If you find any difficulty, please ask me the doubt in the group. Okay. Thank you. Have a nice day. Bye.